Thank you all for being here today. It's really exciting to be in the space with all of you who are so excited about environmental issues. Today, I'm going to be talking about some of the work I do thinking about challenges and opportunities in assessing complex mixtures in relation to chronic health outcomes. Now, in my work, I do a lot with air quality, I do a lot with water quality, but today I'm going to really focus on air quality. And this is an issue that affects everyone. Every single day, we're all exposed to air pollution. But it's also an issue that is quite old. I don't know how well you can see this, but does anyone recognize this painting? What?
It's a Monet.
It is a Monet, correct. It was painted around 1904, I believe.
London Bridge.
It is the London Bridge. And in the back, it might be hard to see with the lighting, but you can see some of the industrial activities and the pollution in the city. And so Monet and many others observed the pollution long ago, right? With all the industrial activities, there was a huge uptick in air pollutants around cities, particularly like London. And then over the subsequent century, all around the world, but including in the United States, we had a number of these smog events. And a lot of this was determined by meteorological conditions, such that there was just much, much higher levels of air pollution compared to what you would normally expect. And some of these resulted in severe mortality. So in 5 days, there were 20 people killed in a Pennsylvania town. That was over Halloween that year. A couple years later, 1966, in New York City, there was another major smog event that killed several hundred people. Right? And people recognized this then, despite the fact that we didn't have particularly complicated study designs and everything else, but it was pretty evident what was going on even then. And so these sorts of events provided the impetus for some of the legislation here in the United States and globally as well. But I'll just briefly touch on the legislation here in the US. The first piece of legislation regarding air quality here was in 1955. Over subsequent decades, these laws were strengthened and revised. And one thing that I think is really important to note, in 1970, EPA was established. Does anyone remember who was president then? Nixon. Very good. And then 1990, the Clean Air Act, as we know it today with the current set of amendments, was updated. And who was president then? Bush. So 2 Republicans. And so I really want to point out here that this is an issue that really, in today's climate, it might be easy to think of this as a partisan issue, but it really isn't, right? This is an issue that affects everybody, and we very much can have joint solutions where players work together and putting, health at the center, which the Clean Air Act really does. And the emission standards are health-based. Whether we actually think that they're rigorous enough can be debated, but at least the idea is that they are health-based. And so people can work together, and has been done historically. We can do it again, right? So I just think that offers a little glimmer of hope here in today's climate. And they've been really effective, right? So what you see here is the declining national air quality emissions between 1990 and 2018. And for many of the pollutants, you see this nice steep decline, which is great. And so maybe the problem's done. Do we have to worry about this anymore? Yeah, unfortunately, we still do. So even today, we see globally that particulate air pollution is responsible for over 4.2 million deaths and 103 million disability-adjusted life years annually. That's a lot of impact, right, globally. And a lot of that is outside of the US. We really have seen impressive improvements in air quality. However, we still have problems within the US, right? Like, for example, Denver, that's where I'm from, so I think this is exciting. And I was just in Denver when this happened. They're now required to do extra monitoring because of the air quality problems there. Or in Australia, I'm sure you've seen all the wildfire coverage. You have huge impacts. You're certainly seeing health impacts from those wildfires in addition to the economic impacts, the biological impacts, and everything else. And then, unfortunately, these kinds of headlines are really common. Globally, you'll see this kind of headline where poor air quality keeps schools closed in various cities. And so this one's very recent, but other times I've given these types of talks, I'll pick one that was recent to then, and these will be from all over the world, really, which is unfortunate. So that means we really are still seeing these impacts. And is complicated. Like, how are we going to continue to improve the situation? Right? The way our national ambient air quality standards are, we have standards for individual pollutants, these criteria pollutants. So it's not all air pollutants, but it's ones that people think are particularly important for health for various reasons. Except that when you are exposed to tailpipe emissions from a vehicle, you're not just exposed to single pollutants, right? You're exposed to a whole mixture of particles and gases. And because you have common sources like tailpipe emissions, like restaurants, like airports, it is very hard to regulate truly mixtures of pollutants. Like if you have a technology that can decrease levels of pollutant A, often pollutant B will be more abundant for various reasons, right? So it becomes very challenging. So as we're going through the talk today, we're going to be referencing some of these different pollutants. So just by way of background, we were talking briefly before about particulate air pollution. And so particles that are less than 10 microns in aerodynamic diameter and particles less than 2.5 microns are both criteria pollutants. And so those are regulated. Smaller size fractions of particles are not regulated, so what we call ultrafine particles that are teeny, teeny, tiny. You can't even make those out on the slide. But the problem is that these particles might be the most toxic size fraction of air pollution. We don't really know. We don't have enough studies yet. They're hard to measure because they vary a lot in space and time. But because they can penetrate more deeply into the body, they can cross biological barriers, we're particularly concerned about those in the health world. So those are the particles. We do tend to look at them by size fraction, though you could look at them by mass or by composition, but most studies look at them by size fraction. And then we have a bunch of gases. This is just a simplified diagram for NOx and ozone chemistry, very, very simplified. And what it shows is that there's a lot of photochemical processes that affect the gas concentrations. We have primary and secondary pollutants. So nitrogen dioxide is one of the criteria air pollutants that we regulate, but all of these are in the air that we breathe every day, right? So does it matter? Well, in addition to what we've been seeing globally with the mortality and disability-adjusted life years, we know that short-term exposures to each of these pollutants is associated with health effects. So based on meta-analyses, I specifically focused on cardiovascular outcomes only because my research focuses primarily on cardiovascular outcomes. I could have given the same slide with a whole bunch of other outcomes, right? So we know that the pollutants are associated with a variety of outcomes, including hypertension, systolic blood pressure, diastolic blood pressure, heart attacks. And this work comes from studies that have happened over the last few decades. One of the first studies, and a very important study, was Six Cities study. Has anyone heard of that one before? So Six Cities study was published in 1993, and they looked at air quality across 6 cities in the United States, and they compared concentrations and mortality outcomes with short-term exposures. And they found that cities that had higher air pollutant concentrations also had higher mortality. And so that was a very, very influential study in helping set the national ambient air quality standards we have today. And then over the years, we've been able to refine our study designs and look at different populations and have better exposure assessment. And so now we can look at a variety of outcomes, both short-term and also long-term. And so if we start looking at long-term exposures, we see that individual pollutants are associated with, again, a variety of chronic health outcomes. Most of this work has been done in the US or in Europe, but we would expect that in some of the developing countries like China or India, where the concentrations are much higher, the health effects might even be worse than what we've seen in these studies here. So it's an issue that we have to deal with. But all these studies have been looking at the individual pollutants. And we already discussed that it's really the mixture that people are exposed to. So how do we start studying that? Well, there's a number of ways that we can think about the pollutants working together to affect people's health. One concern is that maybe these studies that show that pollutant A is associated with health outcome B we think it's really pollutant A, but actually it's some other pollutant in the mixture that you're exposed to. So that's certainly possible because these pollutants are highly correlated. When you're exposed to one of the pollutants, you're often exposed to the other. And so if we really want to know if it's a given pollutant, if that matters for the health standards, we might want to think about something called confounding. And so if you control for confounding by the other pollutants, you can see if that changes your effect estimates. And this comes from one study, and the senior author in the study actually was the same guy who did the six-city study I told you about in 1993, but this one was just published last year. So he's a very influential guy in the field. But in general, you don't really see that the effect estimates change a whole lot in this study looking at all-cause mortality. But it depends on the outcome. It depends on the population you're looking at. So it is important to think about confounding. But that's not really where we want to stop. You might think about interactions. So two pollutants might work together so that the effect that you see when you're exposed to both is either much bigger than you would expect from the additive effects of each alone or much smaller. So that's possible. And there's a number of ways people have looked at this in the literature. One of the simpler ways I've seen people to look at it, but I think it's a rather compelling way in certain respects, is that you can hold the concentrations of one pollutant constant and then see how the other pollutant health effects change. And then you can look at it the other way as well. And so like in this figure, what they're doing is they're looking at the 25th, 50th, and 75th percentiles of each of these pollutants, and then the distribution of the same pollutants, but looking at the two-way interactions. And then what they were finding was that there really weren't a whole lot of interactions for this particular outcome, and we know that because the lines are parallel. So in this situation, there wasn't a lot of interaction. Again, with other outcomes, short-term, long-term exposures, you certainly could, but this is at least one way we can start to study it, which is helpful. And then what we're maybe most interested in, though, is the mixture. So like if you actually have a bunch of pollutants that work together to affect health outcomes, what does that mean? So this, I think, is probably the hardest for us to study. We don't necessarily have great ways to do it yet. There's a lot of statistical methods that have been suggested, but there's not a whole lot of consensus on which is the best way to do it. One of the ways I've seen, and something we can maybe wrap our head around, is that people can think about pollutant day types. So maybe on a given day, one pollutant has particularly high concentrations and other pollutants have lower concentrations. Whereas on another day type, maybe most of the pollutants have sort of medium concentrations. And you can have all these different day types, and this will be determined with a data-driven approach. So they can use something like principal component analysis or other statistical methods to separate the day types. And then what they'll do is they'll relate the day type to the health outcome. And so in this particular paper, they looked at asthma and upper respiratory infections and a number of other outcomes. And what they were doing is they're relating these day types to the health outcomes. And so that's one way we can start thinking about mixtures. But it's hard because if we're talking about this mixture, what does that mean operationally? Like, what are we going to actually do if we say, like, okay, like this day type is associated with a health outcome? Are you going to regulate that day type? I mean, so it becomes very hard to use these results in policy. And so that's one of the challenges that we have in the field, is making sure that our studies are valid, but they're also helpful to people in the real world who need to make policies and everything else. And of course, the situation really is much more complicated, right? So not only do we have the multi-pollutant mixtures, but we also have other environmental factors. We have social and economic factors affecting health outcomes. And so people try to develop all these different statistical tools to deal with the complexity of the situation, but I think this is an area that's very much undergoing a lot of active research right now. And my guess is in 10 years, we'll look back at the studies today and think that they were rather naive, or at least I hope that that's true, because I don't think we have great ways to do this quite yet, or at least we don't know which of the ways that we have available are the best yet. So given all of this, what are ways that we can start approaching it? Well, we can start thinking about how to improve the exposure assessment. That's really important. So anytime you have an epidemiological study, the strength of that study is largely dependent on how well you are able to assess people's exposures. So if you don't get a good estimate of how people are exposed to air pollution, you're not going to understand the health effect of being exposed, right? And so since people are exposed to these mixtures of pollutants, and we want to be able to separate either the independent or the joint effects of these pollutants, we really want to know how we can model people's exposure to these pollutants in such a way that we can take advantage of the times and the places where the pollutants aren't as highly correlated. We know that they are highly correlated overall, but there are these times and places where they're not as highly correlated. So how can we do that? First, a little bit of background. You have to think about the sort of why the pollutants vary differentially in space and time. You have a number of factors that affect pollutant concentration, for example, time of day. So you expect concentrations to be higher during morning rush hour than later in the day because you have more of the source around, right? Similarly, season affects the pollutant concentrations a whole lot because of things like temperature and daylight. And we talked a little bit earlier about how these photochemical reactions affect the pollutant concentrations, and different pollutants are more common during day versus night and everything else. And so that will certainly affect the covariation patterns. And then wind speed and direction. So the farther you get from different sources, presumably the lower the concentrations will be, but that could affect different pollutants differently. And we do see that. So one study that was published, I think, in 2010, looked at how concentrations of different pollutants decayed near major roadways. And so what they found was that, as they expected, that the concentrations of all the pollutants were highest right near the roadway. And for many of the pollutants, the concentrations got much lower very quickly within just a few hundred meters from the highway. But then for some pollutants, you don't see that rapid decay. So the pollutant concentrations are more stable across longer distances. And so we can take advantage of these sorts of spatial differences to think about our multi-pollutant analyses. And we can also think about how those other factors, like season or land use, affect pollutant concentration. So what you see in this figure is a map of Chelsea, right? And so the deeper colors represent higher concentrations. First set of panels here are winter, then spring, summer, and fall. And the top panels are all NO, the bottom ones are all ultrafine particles, which we measure as particle number concentration. And so what you see here is with the colors, they're divided by quartile. So the lowest quartile of exposures tend to be in these areas here in Chelsea, where it's mostly residential land use, some nice green open space, whereas the higher concentrations tend to be where the major roadways are around Chelsea. So that is pretty much what we would expect, which is good. If you pay attention to the legends here, what you'll notice is that the concentrations are very dependent on season, so that you have much higher concentrations, for example, in winter and fall than spring and summer. But the kind of cool thing is that the relative spatial distribution doesn't change a whole lot seasonally. So if I didn't give you which season this was, and I just said this is a map of NO, and I said, and if I just asked you which season it is, you wouldn't be able to tell me. They're pretty similar, which is kind of cool. And that the spatial distribution is pretty similar for NO as it is for P and C, but it's not exactly the same. And it's those not exactly the same points that we're really interested in. Like, why is it different in some of those points? And that's one of the things that we can think about when we start doing those exposure models. Similarly, you can look at other factors like time of day and wind speed and wind direction. So here, what you're seeing is a bar graph of NO2 and P and C. And we're looking just at mean concentrations by time of day and by wind direction. And you can tell that the concentrations are highest in the morning for both pollutants. But there are definitely differences based on the wind direction. And those patterns are not exactly the same for the two pollutants. So again, these are just factors that we can maybe exploit when we're looking at how exposures covary in space and time. And maybe that'll help us actually get at these mixture effects. So if we know what those factors are, now we have to build our models. So how do we do that? There's a number of ways that you can build models. It depends on the spatial scale that you're interested in, the kind of data that you have available. But we're going to be talking about sort of this part of the pathway, right? So in environmental epidemiology, we talked a little bit about how the pollutants are emitted and we can understand those distributions in space and time. And then eventually we start looking at the health impacts. But in the between, we have to figure out how people are actually exposed to those pollutants in the air, right? So that's where we're at. So, so some of the data that I've been showing you and will show you comes from the Boston Puerto Rican Health Study. And so one of my colleagues drove not this vehicle around, but the previous Tufts Air Pollution Laboratory around Boston and Chelsea along those lines that you can see in black many, many times over lots of days of the week and lots of all the seasons, different times of the day. And we were able to monitor the air quality. So we have really good spatial resolution of the data because we drove all around these two cities. So we know what the pollutant concentrations are at each of these places around the two cities. We also have time series data from the pollutants, from EPA monitors, and then some of our own data as well in both study areas, which is really helpful. So now we can start building models using these data. And the way that my colleague built the UFP models and I'm building the NOx models is with these land use regression models. So what we're trying to do is we're using these things about the area that we know. So we know that concentrations are going to be higher near major roadways, lower near green space, things like that. So we can use our understanding of how the pollutant should vary in space and time, and we build up these models. And we're going to use the time series data from those fixed sites, and then we're going to use some of the spatial information we're getting from the mobile monitoring campaign. And then what we're going to do is we're going to take these measurements that we obtain. So this is, each of those little triangles represents a measurement that was obtained along our monitoring route. And we can compare the concentrations at those spots to the concentrations at the fixed site. And we might expect that concentrations right near this major road, represented in red, would be higher than at that fixed site. And maybe the concentrations here that are near this nice green open space are going to be lower than at that fixed site. And we might expect that to be true regardless of time of day or season or anything else. And so what we did was we calculated what we called spatial factors. So we just divided the concentration at that on-road site to the fixed site. And we said, let's just say for sake of argument that here the concentration was twice as high as at our fixed site. Whereas here maybe it was a third as high as at the fixed site. Okay, great. So those are our spatial factors. And then we can model those spatial factors across the whole study area. So this is again Chelsea. And the deeper blue areas have higher spatial factors, and the yellow areas have lower spatial factors. And this map, if you remember the ones I showed you before, sort of looks like the ones that you saw earlier, that the lower concentrations are in the residential areas, the higher concentrations are where there's major roads. So this isn't a huge surprise, and that's how we built the model. But then if you know the spatial factors across the whole study area, then you can take, say that this spatial factor represents 2. Then at any given time, you have the time series data, so you have the fixed site measurement. You can say like, okay, if at that fixed site it says that the concentration is 50 parts per billion, but we know that this spot's expected to have concentrations twice as high, you just multiply. So now at this point in time at that spot, you think the concentration's 100 parts per billion. So this is a really nice way to figure out what people might be exposed to in places and times where we don't have air quality data measurements, which of course is going to be true when you do these large long-term studies. You're not going to have air quality data for all the people at all the times, right? So you need to do these sorts of models. So that's very helpful. And the nice thing is that the models perform really well. We have the mobile monitoring data from 2011 till 2015, but we have health data back to 2004. So we need our models to be able to predict people's exposure earlier in time. And they actually do that really well. So our predictive values you can see here at a fixed site that was not used in model development, you can see in green, and then the measured values at that fixed site are in orange. And the cool thing is that the concentrations are almost identical, and it captures this time series really well, which is basically just telling you that the temporal trends matter probably a lot more than the spatial trends for this. But it's nice to know that we can do this sort of modeling. And then once you have these models, what you're doing is you're predicting ambient exposures at a given place, right? But what's traditionally been done in these air pollution studies is that you predict people's exposures at their homes. So you have what we call this residential average, which is fine, except that most people don't just sit on their front porch 24 hours a day, every day, right? So, you're all at school, or you're commuting, or whatever you're doing. So we want to account for where people spend their time. And so that's where we get this time activity adjustment. So, maybe if you're commuting, we'll assume that your exposure is a little bit higher than what they would have been at your home. Or maybe if you're at school or work, they're a little bit lower if you're indoors. But if you have a certain kind of job where you're outside a lot, maybe they're higher. So we can make these sorts of adjustments. And we also want to make adjustments for how people, like how active people are. We know that age, sex, weight, and physical activity all strongly affect inhalation patterns. And so we want to know not just the ambient concentrations, but we want to get a little bit closer to the biologic dose. Clearly, the particles in the air are not going to affect your health unless they get into your body, right? And so if we can think about the inhalation rate, you get a little bit closer to what people are actually exposed to in sort of this meaningful biologic way. So you can make all these sorts of adjustments, which is great, but we still have the problem that we might have really good exposure assessment for 2 or 3 different pollutants, but now what are we going to do about it? And how are we going to actually ask the questions from an epidemiologic point of view? Right? So we have really good exposure data. That's awesome. We need that. Without that, you can't really do the epi studies. But we've talked a little bit about some of the challenges in thinking about looking at mixtures and health effects. And if we look at those multi-pollutant day types, what does it actually mean? Like, how consequential is it to actually look at a multi-pollutant day type and then go tell a policymaker that a day type with concentrations that are all sort of medium is better than a day where all the concentrations are sort of high? They'd be like, yeah, that's great. What are we supposed to do about that? So we really need to ask questions that can be translated into real-world action. So, in the field, we might ask these broader questions like, what are the long-term health effects of the smallest size fraction of particulate matter? But that's not really a very helpful question, right? It's not specific enough. It doesn't tell us what would happen. If we know the answer to that, it doesn't tell us what to do. We want to be able to ask questions where, if we know the answer, then there's a next step in the real world, right? And so these are all important questions, but we need to refine these questions a little bit. So how do we refine the questions? One of the ways that you can do it is you can think about what sort of randomized study you would do if you could have done it. So in the air pollution world, you're pretty much never going to do randomized studies. There are some ways you can do it. You can look at interventions with air filters and things like that, but sort of in this broader context, those are very, very hard to do. But we can think about, in this ideal world without all sorts of real world constraints, what study would you do? And if you were doing that, what would the intervention be? So if we change air quality in a certain way, like we reduce the concentrations of this set of pollutants but not the other set, then what would happen? So you can start asking these questions that can be operationalized later. And so we want to define really good questions so that you can have meaningful answers. And this is something that is actually sort of surprisingly controversial right now in the field. There's a lot of, I think the general principle is not controversial. People want to have real world impact. How you go about doing that at this point is somewhat controversial, and different epi methods people have very different views about how to go about doing this, and also how you would apply it in the environmental health space. I think the application of this idea, where you're thinking about what the trial would have been, is maybe a little bit more straightforward in certain fields of epidemiology than it is in environmental epidemiology. So this is something that, while maybe intuitive at some level, is actually very hard to operationalize and has not really been done a whole lot in the field yet, though I think there's a lot of movement towards it. But when we're doing that, we really are trying to think about this very complex pathway, and that's why we have to ask such good questions, right? So now I'm going to ask you guys, what would you do if you wanted to design the study? I know a handful of you guys have taken epidemiology, but you don't actually have to know a whole lot about epi for this. That's okay. What kind of study would you guys want to do? Or what are some key features of your study? would you want a study design where you could assess exposures prior to outcomes developing? So that you know the temporal sequence. So you would want that. And a lot of study designs let you do that, and a lot of study designs don't. But you really want a study design where you have this prospective exposure assessment where exposures are assessed prior to outcomes developing, and that's important so that you don't introduce some of the biases about how people assess exposures and report outcomes and everything else. So you want those kinds of prospective study designs. Who would you want in the study? If you want this to maybe affect US policy, who needs to be in your study? Yeah.
I know the correlation between these projects and preterm birth. So I would say let's go with babies because that's very impactful to policymakers.
Sure.
And it's easy to measure outcomes. Look at structural ultrasound. What is the birth predicting based on that? What is the happen? What is the solution?
Okay, so we're going to have babies in our study. Should all those babies live in Boston?
I think we should do a gradient.
Okay.
Urban to rural.
Okay, urban to rural. And should it only be in like mass urban to rural, or should we include maybe other parts of the country?
How much money do you have?
I don't know. You want to give me a lot of money? I'd love to do a bigger study.
Much as you can afford.
Yeah.
Other cities would be great.
Right, and so that's one of the reasons actually that the Six-City study in the early 1990s was so influential, is because it really was kind of sort of at least representative of nationwide exposures. I mean we could quibble about that, it's not totally true, but they were at least trying to get at this idea of the exposures do differ in different places, and the composition of the air pollutants might differ in different places. And so theoretically, if we had the money to do it, we probably do want this nationally representative kind of study, though you probably want to underrepresent certain vulnerable populations, right? So you're worried about babies. Well, we know that there are huge racial disparities in birth outcomes, so you might want to overrepresent communities where you might expect worse health outcomes to make sure that you can actually meaningfully study what's going on so that we can do something that would help those populations, right? What else might you need to assess? So it's great to say like, okay, an air pollutant is associated with a health outcome, but that alone doesn't tell you much about causality. You might be concerned that there are other factors that are obscuring that relationship. What are some of those other factors we might want to have to measure? Yeah?
Kind of similar to what you just said, but looking at like socioeconomic, race, ethnicity, other things that we know impact health outcomes.
Exactly. So there's a lot of things that go into that. And it will depend a little bit on what the actual outcome is, and if you want to look at short-term or long-term exposures and everything else, what else you need to measure. There's going to be a whole host of other things you need to measure. And then how do we analyze our results? So this is definitely an open question, right? I showed you that slide where there's a whole bunch of approaches that people use, like and under each of the three major categories of like dimension reduction and everything else, there's a whole set of analytic techniques you could theoretically use. So it's not as simple as just collecting the data and then running a simple linear regression. I mean, maybe that works in a certain situation, but more likely than not, that's not going to be enough. We have to account for these complex data structures. Probably we're going to introduce bias into our study. If we really do have these sort of prospective studies, we're probably going to have some loss to follow-up. And the people who drop out are not usually very similar to the people who don't drop out, right? That can bias your study. Or maybe we assess certain people's exposures better than other people's exposures. So you wanted us to do urban and rural. Well, it's a lot easier to accurately assess people's exposure in urban areas than in rural because we have more air monitoring stations. Right? So we're going to have all these different biases. We know that, but if we can at least try to quantify the impact of the bias, that might be really helpful for policymakers in saying like, okay, even if we have this amount of bias, we still think that this relationship holds and we need to do something, right? And then this is also very important. How do we communicate the results of our study? It's not enough that we just did our study and published our peer-reviewed journal article. If you actually want to have a real-world impact, you have to do something about it, right? So there's a whole field of health communication, which I think is very, very important. And I think scientists in general need to do a better job of health communication. So how do we share what we're learning in a way that's meaningful to different populations and different stakeholders? So I just wanted to wrap up saying that, as you guys heard, that I'm a triple jumbo, and I started doing research here as an undergrad, which was very important in the trajectory of my life, and that I think that even had I not gone into academia, the skills and stuff that I learned were very important, I think, transferable to other fields. So I encourage you, if you're interested, to reach out to faculty and look at the many, many resources around campus to get involved in research if you're interested. People are excited when students are excited about their work, so don't be shy to reach out. I want to thank funders and lots of people, including John, who've been very influential in this work. Thank you, guys. Are there questions?
Thank you so much for this big preview in this fascinating world. Are there questions?
Hi, you mentioned the effects in Chelsea, studying them,
Yeah.
and being near the roads. And one of the things that everybody may not be aware of here is that as far as air pollution from airplanes come, Tufts is a target for that. They used to spread the planes from Logan in a wide dispersal direction. But several years ago, when they decided they wanted to greatly expand the operations at Logan Airport, they came up with a plan called RNAV, which changed it from like this green dispersal pattern down to 4 hyper-concentrated highways in the skies. So on days with northwest and northwest winds, which are occurring far more than half this time of year, you'll see planes coming in right up over Alumni Field. That's right over here, and then spread out onto these other 3 very narrow bands, one along the north part of campus here, one along the south, and one right down the middle. And it's crazy. They claim this RNAV thing is a green solution, but what kind of green solution is it that hyper-concentrates all of the pollution onto just a couple of people here? And the reason they're targeting Tufts is because in their studies, they say that it's, as a college, just like schools, the West Somerville Neighborhood School, that it has a 0 residential population. So there's no people who are actually affected here, which is obviously crazy. Any reaction to that? Oh yeah, I just wanted to say, if you're concerned about this issue, because it really does affect us and it's getting worse and worse, because Delta and JetBlue and American Airlines, they've been expanding massively, and you can read about their massive expansion plans in 2020. LoganNoise.org is a website where you can learn how to complain and get involved in this. Thank you.
Okay. No, it is interesting to see that there are definitely going to be populations that are differentially affected, and airplane emissions, I don't think even like maybe 10 years ago people talked a lot about airplane emissions in terms of health outcomes, but now people certainly are. Malakshi Huda is here. She's done a lot with airplane emissions at Tufts, and it is an issue that people have started to think more about, and is important to think about which populations are affected and how they might be affected and what we might be able to do about it.
I wanted to come back to your 6 cities comments, and I'm assuming that temperature has a huge effect on both your exposure, how likely the reactions, and the health outcomes. Is there a general pattern that you would say is true, that the warmer it is, the worse it is? So if you're in LA, you're worse off than if you're in Denver, and which is you're worse off if you are in Chicago? Or is it just way too? Is the temperature effect too hard to quantify?
No, we definitely see temperature effects on air pollutant concentrations. The highest concentrations tend to be in winter, like those really cold winter mornings, you get really high concentrations. But temperature does have an impact on both exposure and health outcomes, and so it is something that we need to take into account in our modeling, and is something that, of course, is becoming increasingly important with climate change and everything else, and people are exposed to much higher temperatures on average.
I have a question about skills. So you were talking about models, for example. What kind of skills do you need to have to develop these methods?
Depends on which set of models you want to do, but you definitely need some statistics skills. It will be helpful to know at least one, but preferably more than one software to do the statistical modeling, because you're not going to do this by hand. If we were doing this, I don't know, 30 years ago, you'd have to have a pretty high level of math. Now you kind of don't, depending on where you want to be. Like if you want to develop the methods, you do, but if you want to use the methods, you mostly just have to know what assumptions go into all the models and everything else. But I would say if you're going to do stuff on the exposure side, you want to know something about the environmental science, and you always want to know something about the content behind the model, because you do really want theoretically grounded models. So if you're going to do the health analyses, you really want to understand as much as you can what the likely causal structure is between the exposures and the outcomes and any other variables that might affect that relationship. So you do, in addition to sort of those statistical skills, want some content expertise in whatever it is that you're modeling. I mean, you're not going to be the expert on everything. There's a reason that we always do science in teams. You know, so you don't have to have all the skills, but you have to be able to learn at least some subset of these skills.
Wonderful presentation, and thank you so much for including the pitch for the importance of student research. I want to follow up on Coco's question by saying there may well be students in the audience who are interested in sort of this, sort of how do they work in this field? They want to help with air pollution, sort of. And you've talked about environmental communication. You've talked about just now about a lot of statistical tasks. What are some of the sort of paths and possibilities you see for students? What would you recommend they take as undergraduates? Where are some of the different directions you could see people going for masters?
Sounds good. Take anything he teaches. So if you really want to do stuff in air, it would be helpful to know some of the environmental chemistry and the air pollution control that is taught in civil environmental engineering. Let's see, I would take epidemiology if you're interested in this. I would take biostatistics, or you could take you could take statistics or biostatistics, but the biostatistics tends to be a little bit more focused on these kinds of analyses, but all the same basic principles. Other classes that you should take. I think the more science classes you take, the better. I took a ton of biology and chemistry as an undergrad, and that's only ever helped me for sure. And then in terms of other out-of-class experiences, I mean, I think it depends a little bit on what you're interested in. You know, some people want to go work for government, which is awesome. You can do that. Some people want to, you know, get involved like in nonprofits and doing some of the environmental activism, which is excellent. You know, some people want to get involved in healthcare, and you know, maybe you're going to be a clinician who really thinks about social determinants of health and environmental determinants of health. And so I think there's a lot of different pathways depending on what you're interested in. And you know, I think that reaching out to faculty who might be doing stuff that you're interested in, or who might know people in fields that you're interested in, is a really helpful first step, because there's a lot of opportunity in the Boston and larger New England area for students to get involved with.
Very interesting talk, Laura. Thank you so much. I have a comment and a question. So to your point about the jets, really interesting summary you gave us about the highways and the sky. What we've observed in our research, and some of which Laura's talked about, is that a lot of the pollution that you get at ground level is not from jets taking off, but from jets landing, because they're coming in at a much shallower angle and they're much closer to the ground for a longer period of time. So just keep that in mind. So if you're worried about super high exposures, living here on campus, it's usually when planes are landing, and they don't land. Luckily, they don't land over campus that often. But it's the noise you experience when they're taking off, because they're much, much louder. So you can definitely hear the highways in the sky.
And maybe just a point to make that, because there's been some research, there was an article last month in the Boston Herald about research at Massachusetts General Hospital, where they had located the structures in the brain with the amount, I'm not sure I'm saying that right, but essentially, one key quote that I got out of that is every 5 decibel increase in environmental noise is associated with a 34% increase in cardiovascular events, heart attacks, and strokes. So those are real health problems. There are a lot of people who just try to categorize the airplane noise as being an annoyance and that people are being too sensitive. But no, your rate of heart attack, stroke, and cardiovascular events goes up
34% within a 5 decibel increase.
Right, so there's another study for you to do, Laura, when
Okay.
you get older.
Great.
So here's my question. So with the complex mixture effect, wouldn't you have to increase the size of your study population significantly to be able to tease all that out?
Yeah.
So you talked about the Boston study and Chelsea, so those are your two study areas. Do you have a large enough population, enough measurements per person, enough time passed between measurements and so forth, that you're going to be able to see the health effects that you're hoping to see with your complex mixture analysis?
I think within the Boston Puerto Rican Health Study, we really are only going to look at a couple of pollutants. Ultimately, it's not going to be like, it'll be like 2 or 3 pollutants. So I think with that, we could do some of the interaction analyses. So those we would have enough power to do. If we really wanted to do this like complex mixture analysis, I don't think that sample size is big enough.
How big would it need to be?
Depends on the outcome, the variability in exposure.
You talked about NO2 and ultrafine particles.
Yeah.
So what health outcome are you looking at?
Well, we've been mostly looking at cardiovascular health outcomes, which in that population, well, so the Boston Puerto Rican Health Study is a particularly important population to study. In that population in the Boston area, only about half of our participants at least had more than a high school education, or more than 8th grade education, excuse me. About half of our participants had things like diabetes, hypertension, depression at baseline, so at the first study visit, which means that looking at incident events in this population is very challenging because we're starting off with such a sick population, so that even if there's a relatively high rate of these events, because this sample isn't huge, because we only followed them for about 6 years on average, we're not going to see a ton of new events, so it'd be very hard to study something like heart attacks in this population. We can look at something like changes in blood pressure or continuous measures. So something like that we could look at in this population. We wouldn't be able to do something like incident diabetes, though. We could do glucose. So you can do the biomarkers, but you can't really do the incident outcomes in that population because the sample size is important.
Just curious what the sample sizes you have, like how much bigger would it need to be? How big are you now? Because I'm just kind of curious.
So that population, we have about 1,000 people in Boston and Chelsea at least one time point. Other studies, a lot of studies are sort of in that in that magnitude, give or take. Like the Framingham Heart Study is also in a similar, same order of magnitude. They have probably a few thousand, depending on which cohort you're looking at and which time periods. With a few thousand, it might be a little bit easier. And they were a healthier population to start, so it's a little bit easier to look at incident outcomes. So it depends a little bit on which population you're looking at, how big the sample needs to be, and how you want to do these analyses. How good, it depends a lot on how good your exposure assessment is, for sure. I mean, there's not, I mean, I'm sure people are sort of looking for a number, but there really isn't a number. So, sorry. It's not 10. It's in the very minimum, probably thousands. But more is generally better. Not always, but often. More is also more expensive, so that's a problem.
Any other questions? Okay, well, let's thank Dr. Corlin once more.